All right, thank you. So, hello everyone, and today database tuning tools that read the manual. And that relates to the good old saying, when all else fails, read the instructions, which somewhat refers to the fact that people tend to read the manual as a last resort, when it would probably have been better to read the manual at the very beginning. And that is certainly true for the domain of database tuning. We want to find good parameter settings in order to optimize performance for a given workload. And of course, we can start trying out different parameter settings and observe what kind of performance we're getting from that. But probably it's going to take a long time to find really good parameter settings. And also some of the parameter settings might have undesirable side effects that are difficult to observe. So probably it's a good idea to first have a look at the database manual and perhaps a couple of other related documents, such as blog entries about database performance or discussions on a DBA Stack Exchange and such forums. And that will give us a much better starting point for database tuning. Now, what I'm saying so far, it seems to primarily apply to human database users. But in this talk, I want to actually transfer this piece of wisdom to the domain of automated database tuning with the goal to teach those automated tuning tools to read the manual. And until a couple of years ago, it would have been difficult to realize that. It might have been overly ambitious. But now over the past couple of years, there has been a lot of exciting progress in the domain of natural language processing, which actually makes that possible. And even if you are not regularly following research in natural language processing, you might have come across a couple of headlines like the one over here in newspapers such as the New York Times, which reference recent advances in natural language processing as incorporated, for instance, into large neural network such as the GPT-3 model. And those articles, they outline various new use cases ranging from writing newspaper articles to trying to predict the football results. So there's a lot of excitement around natural language processing. And one of the key advances that has enabled those advances, that is the introduction of a new neural network architecture, such as the so-called transformer model. And one of the advantages over prior methods is that it makes it easier to scale up a training to really large scales. And that has in part enabled the generation of very large pre-trained language models, such as GPT-3, which are very large neural networks with hundreds of billions of parameters. Now, those neural networks for natural language processing, they are typically, first of all, trained in a so-called pre-training step. And for that, we use tasks for which large amounts of training data are easily available without any manual labeling. For instance, I could be trying to predict a missing word in a text or trying to predict how sentences continue. For that, we can, of course, use arbitrary text from the web as training data. Now, this pre-training step is extremely expensive. It can cost millions of dollars to train one of those models, but the good news is we only have to do it once for each model. And if we want to specialize a model to do another task within the domain of natural language processing, we can do so by a process called fine-tuning. For instance, if we want to teach one of those models to translate natural language questions into SQL query, we do not start training from scratch, but we start training with the pre-trained model, and then we need orders of magnitude less training samples and less computational overheads in order to get good at more specific tasks. Now, I'm proposing to leverage this kind of technology for the domain of database management system tuning. So for clarification, what I mean by that in the following is we are given an input, a workload to optimize, and a performance metric such as latency or throughput according to which we want to optimize. The output of database parameter tuning is a configuration, which means a mapping from a database system parameters to specific values. And our goal is to find a configuration that maximizes the performance metric for the given workload. Now, there has been a lot of interest recently in automating this process. There have been lots of papers in the database research community. There's also now a recently founded startup which focuses on this problem and addresses it with machine learning. The motivations for using automated tuning in this domain is, first of all, that the number of parameters to tune in those database management systems has been continuously growing. And if you look at a system like Postgres, for instance, it has many hundreds of tuning parameters. And the settings for those parameters are very relevant for performance. In general, if you want to maximize performance for a given workload on a given platform, then the default settings will typically be significantly suboptimal. All right. So currently, most of those existing approaches to automated database parameter tuning are based on machine learning in some way. One representative approach is, for instance, the recently proposed DBG++ method, which we will also see as baseline in the experiment. So it takes as input a workload and a metric to tune for. The output is the best configuration found until the tuning time limit. And in order to find good configurations, the system uses a trial runs with the database management system that we are optimizing for. And after setting a specific configuration, it will execute the workload to optimize in order to measure the performance. And in order to decide what to try next, it uses a reinforcement learning approach. I will introduce reinforcement learning in a little bit more detail later, but it is essentially a very principled trial by error approach. Now, this is somewhat representative of what database parameter tuning methods are currently doing. It comes with a couple of limitations. First of all, we typically need significant tuning overhead. So those approaches often expect to be able to try out hundreds of configurations. And depending on the workloads that we are tuning, that might actually take days to do that. Also, many of those approaches, they implicitly assume that as additional input, I'm providing them with a small subset of relevant database parameters to tune, as well as with parameter-specific value ranges to consider during tuning. And in order to identify relevant parameters and reasonable value ranges, I already need some database expertise, which lay users may not have. Finally, and I'm putting this into parentheses because we have come to not even expect that from database tuning tools, those tools correspond to black boxes from the user perspective pretty much. So they will propose certain parameter settings and perhaps tell you what kind of performance you're getting with them, but they would not be able to provide some kind of explanation about why specific parameter settings work better than others. The information that we need in order to overcome those limitations, in my opinion, is already out there in the form of natural language text and written in the database manual, but also in various blog entries about a database performance, in forum discussions on forums such as DBA Stack Exchange. So there's a lot of knowledge that is already out there, but in order to access it, we need to use natural language processing. Now, following this line of thought, I have recently proposed first a simple prototype of a system which exploits tuning documents for database tuning. So this system leverages a collection of tuning text documents with relevant information about a specific database management system. Then it uses text mining in order to extract specific recommendations for setting specific parameters from those text documents, and then it proposes one single configuration based on those tuning documents. In order to extract the recommendation via text analysis, it either uses a keywords-based approach, which is relatively simple and merely used as a baseline in this paper. There's also one approach that I propose, which is based on supervised learning, exploiting a fine-tuned version of those pre-trained language models that I have introduced before. Now, without going too much into detail on this system, there's perhaps a couple of limitations that are already apparent from this outline. And by the way, I will use those two variants of the system, the keywords-based extraction approach and the supervised learning-based approach as baseline in the experiments. Now, the problem with this is that this system completely trusts in the tuning hints that it finds in the text documents, even though there might not be always optimal for a specific workload, a system, and a metric. So since we only use tuning text as an information source, we cannot specialize to a new workload that we are currently trying to optimize. And also as a side note, at least the supervised learning approach, which works significantly better than the keywords-based approach, it still requires a number of manually labeled training samples, which are difficult to obtain for this domain because manually labeling hints often require some degree of database expertise. Now, in order to overcome those limitations, I will discuss DB-BERT in this talk, which is a system that uses both sources of information. First of all, it mines text documents with information about a specific database management system in order to get a good starting point for tuning. And then it uses reinforcement learning and trial executions in order to get from there to a specialized configuration that works well for the chosen workload and performance metric on the platform that we are currently tuning on. Now, the type of hints that we will be interested in the following are some of the hints that you see here, for instance, which are taken from the Postgres manual, but also from different blog entries about a database performance. The first hint, for instance, proposes a parameter setting that is relative to the amount of main memory that we have available on the system that we are currently tuning. The other hints propose absolute values as parameter settings. The first two hints explicitly mention the name of the tuning parameter that they are referencing. The last hint is more implicit. It doesn't directly mention the name of the parameter. So first of all, it would be up to us to figure out that this hint actually refers to the max parallel workers parameter of the Postgres database management system. And in order to use those hints for automated database tuning, of course, we need to extract some more formal representation of those hints from those text documents, like the one that you see here, for instance. Here we express the recommended value for the shared buffers parameter as a function of the amount of main memory available. For the other tuning hint, we have absolute value recommendation. So if we substitute the amount of main memory that we have available in our current system, then we can get to concrete value recommendations for all of those parameters. Now, those parameters over here and many others correspond to a certain template for a parameter hint. This is the scope of hints that we will be considering in the following. So generally, we consider formulas that are assigning to the parameter a recommended value, which integrates a value that is explicitly mentioned in a text document, as well as potentially some values that are derived from system properties, such as the amount of RAM, the amount of disk, and the number of cores. And then finally, we give the system some power to deviate from the proposed values by multiplying the proposed values by a factor between 1/4 and a factor 4. So we can significantly deviate from the recommended values, but if we want to deviate by more than factor 4, then perhaps we want to disregard the corresponding hint entirely. This is the DB-BERT system in a little bit more detail. As input, it obtains a workload to optimize as well as a metric that we want to optimize for. And that is particular. It also obtains a set of natural language keywords as input, which describe somehow the tuning goals or the tuning setup. In the first step, it uses those natural language keywords in order to retrieve relevant documents from the web using the Google Search API. From those documents, we will extract the more specific hints, where each hint corresponds to one specific value recommendation for a specific parameter. And then we use a simple heuristic in order to determine a priority among those hints, meaning the order in which those hints will be considered in the following processing stages. So at this point, the hints that we have are still expressed in natural language. So in order to use them, we first have to translate them into a formal representation. So that is the next step that we do. We try to translate those hints into a formula of the type that I have introduced on the previous slides. Then we might decide to deviate from the recommended value within a certain bounds. And finally, we need to assign weights to those hints, which will become important in case of conflicting recommendation for the same parameter. And then those weights will decide which of those hints will get prioritized. And I think there's a question from Alan. Yes, please.
Yeah, so look, thanks very much. I'm just wondering, the format you showed for hints was essentially a single, an equation for each hint. Correct. A lot of the things that I know about in sort of manuals and so on, they're contingent. They say, if the system is bottlenecked on this, then set a parameter like this. Do you have an extension of your language that includes that sort of aspect?
Okay, very good. So one could probably try to extend the natural language analysis in order to also figure out specific scenarios in which those hints apply. Here, this system essentially decides itself which of the hints it will consider. So since it uses reinforcement learning coupled with natural language analysis, it would over time find out that there are certain keywords, for instance, in the hints that hint at this hint being less relevant. For instance, if we're tuning a Linux system and we have a couple of hints that are specific to Windows, then probably applying those hints will not improve performance. And then over time, the system can figure out which of the hints are more relevant. So in that sense, yes, we will figure it out, but it would potentially take a couple of iterations to figure that out.
Related to Alan's question, the system, once the first bottleneck has been fixed, for example, I don't know, you've increased the buffer pool sufficiently, so now your CPU bottleneck. Some of the hints that were not relevant until you increase the buffer pool sort of come back into play after you've addressed the bigger problem, and now you're down to the second biggest problem.
Right. So in general, I mean, the system is searching for a good combination of parameter settings. So eventually it will converge to parameter settings, to a combination of parameter settings that work well. So if indeed like fixing the buffer pool issue doesn't improve performance by a lot because afterwards we are CPU bound, then the system would ultimately find that out and converge to a configuration that fixes both of those issues. Of course, if there's like some decisions that initially look good, but then later turn out to be bad, it could make the search space more difficult to search for the system, so it might take longer. But in principle, the system searches for a combination of parameter settings that optimize performance. So that would include multiple, like fixing multiple problems, basically.
So one question is, what if you get the hints wrong? For example, if you, let's say we want to set memory, right? There are many memory-related parameters in Postgres, like working memory, like shared memory, and so on and so forth, right? What if you assign one hint to a wrong parameter? Would that be considered?
Okay. So I think that, I mean, maybe some of those questions I think might get resolved by describing in a little bit more detail the learning process. So, I mean, in general, the system will iteratively interpret those tuning hints. So we don't make any final decisions. We are always able to revise those decisions over the course of optimization.
Okay, makes sense.
All right, but those are great questions. Let me quickly give the full overview of the system and happy to answer any questions after that as well. Okay, great questions. All right. So we have now translated natural language hints into a formula. We have potentially decided to deviate from the recommended values, and we have decided to assign weights to those different hints. Now, based on the decisions that we have made currently, we can construct some configurations, meaning assignments from multiple parameters to specific values, and we can evaluate those configurations in trial runs and benchmark performance according to the metric that we care about. Now from that, we can learn to make better decisions in the next iteration, because this second phase of the system here is actually iterative, and we will keep iterating until the tuning time runs out. In each iteration, we will consider some subset of parameters and make decisions, construct configurations and evaluate them. And from that, we learn to make better decisions in the coming iterations. So there's one pre-processing stage that only happens once per tuning session. And then there's the learning phase, which happens iteratively until a user-defined tuning time limit runs out. The result of the system will be the best configuration found until the time limit. So in the following, I'm gonna describe those two phases of the tuning process in a little bit more detail, starting with the pre-processing phase. Now, intuitively, what we want to do in pre-processing is we start from a set of natural language keywords, then we use Google to retrieve relevant documents. And from those documents, we extract text passages that might potentially contain tuning hints. Now, from each of those text passages, we might extract one or multiple hints, where each hint recommends one specific setting for one specific parameter. And finally, we will use a heuristic in order to prioritize those different hints that we have extracted, determining the order in which they will be processed in the following processing stages. Now, let's see those different steps in a little bit more detail. So it starts with querying the web based on the user-provided keywords and trying to find passages that seem to contain interesting tuning hints. We split up the text documents that we find into a number of tokens that can be processed by the natural language models that we use in the following, and use a simple heuristic to filter out text passages that cannot contain any tuning hints. Now, based on that, we want to extract the specific tuning hints from those text passages. And one of the challenges there is that sometimes those tuning hints don't explicitly mention the name of the parameter that they are referring to. For instance, if you consider this hint over here for the Postgres database management system on the right upper corner of the slide, utilize up to 6 workers, it doesn't explicitly say which parameter it refers to. Now, in order to resolve those implicit references, we use a relatively small pre-trained language model, the DB-BERT model, which is relatively cheap to apply. And we use that in order to calculate so-called embeddings, meaning a vectorized representation of the names of all database system parameters, as well as of the tuning hint text. By comparing those embeddings, we can identify likely parameters that are implicitly referred to. Then we can use a question answering approach in order to extract from this larger text passage the relevant text snippet, which recommends the specific value for the parameter that we are currently looking at. And here on the hint on the bottom of the slide, we have marked up the parameter name, which was implicitly referenced, as well as the recommended value for that parameter. Now, we have specific tuning hints after this step. And in a simple approach, we could just use a sophisticated natural language analysis in order to translate all of the hints that we found into formulas. And after we have done that, we could start to execute trial runs. Now, the problem here is that natural language processing can also be expensive. So if we wait for long until we make our first trial runs, then it will take a while until we can return the first configuration to the user for which we have actually benchmarked performance. We want to avoid that and probably prefer to mix up natural language processing with trial runs. So we will process a subset of natural language hints, and based on that, construct some first configurations and benchmark them, then process more hints and construct another configuration to benchmark via a trial run. The problem here is that perhaps we don't have the relevant hints first, so it might actually take a while until we come to the most interesting hints that allow us to get a significant performance improvements. And it is hard to tell a priori whether a specific hint is relevant for performance or not, but at least as a rule of thumb, we can say parameters of the database management system that are frequently mentioned on the web, they tend to be more relevant for performance. So we could use a simple heuristic saying that we will first of all treat those hints which refer to frequently mentioned parameters because we believe that they are more relevant for performance. The problem here is that we typically find many hints about those frequently mentioned parameters, and there's some kind of diminishing returns effect. If you already have seen 100 hints about the shared buffers parameter, then probably we won't learn that much more by seeing more hints. So as final heuristic, we use a heuristic here where we first of all prioritize hints about frequently mentioned parameters, but we bound the number of hints that we consider for the same parameter before switching to another parameter. So this is a relatively simple heuristic, but it is cheap to apply, and it decides the order in which those hints are processed in the following stage. Now, the following stage is the learning phase, which corresponds to the steps marked up in red here. The result of preprocessing is essentially a list of hints that are ordered according to a heuristic, but those hints are still expressed in the form of natural language text. So before we can use them, we first have to translate them into a more formal representation. Now, besides that, besides translating the hints, we also want to decide how far to deviate from the recommended values in those hints and how to assign those hints to weights, which will become important in case of conflicting recommendations for the same parameter. So let's make that a little bit more concrete by a little example. So in each iteration of the learning phase, we would consider some subset of hints expressed in natural language, such as the hints that we will see over here. Two of them refer to the shared buffers parameter. One refers to the max parallel workers parameter. So as a first step, we want to translate those hints into corresponding formulas. Here, two of those formulas, they are relative to a system property, which is the amount of RAM available. Now, if we substitute that by the amount of RAM that we have on our current system, we can resolve those equations in order to get concrete recommended values. So here I'm assuming that a system on which we tune on has 16 gigabytes of RAM. Also, we might decide to deviate from the recommended values by multiplying those recommendations by a factor. And finally, we need to assign weights to those different hints. Now, based on all of those decisions, we can aggregate all of those hints into one or a small set of configurations which assign specific values to those parameters. Then we can benchmark those configurations according to whichever metric we are optimizing for. For instance, it might be the transaction throughput. So here we find which transaction throughput we are getting when using this combination of recommendations. All right, so maybe as a first idea, one could think of using some kind of supervised learning for this, but that is difficult because first of all, it would be difficult to scale up the generation of corresponding labels because crowd workers, for instance, often don't have the required database expertise. More importantly, figuring out what is the best way to deviate from the recommended values and what is the best way to assign weights to those hints, that is actually dependent on the specific workload and system that we are tuning for. So we couldn't do this a priori. And because of all of that, we probably want to use an unsupervised approach instead of a supervised learning. Now, One framework that is generally popular in the context of automated database tuning, and which I will also use here in the following, is reinforcement learning. And in reinforcement learning, we generally assume that we have an agent which manipulates some abstract environment. And the way the agent manipulates this environment is by applying so-called actions. For those actions, we are getting observations that the agent can use in order to decide which action to apply next, as well as reward values. And the goal of the agent is to maximize the reward it receives, because while at the beginning, it doesn't know yet which sequences of actions will lead to optimal rewards. Now, more precisely, I use a deep reinforcement learning in the following. So the actions of the agent are controlled by a neural network. Now, this is the general scenario of a reinforcement learning. When mapping this to the specific problem here, then the agent, that is, of course, the DB-BERT system. The environment is characterized by workload and system properties, and the neural network that we are using will be one of those pre-trained language models which is focused on text processing. Now, actions correspond to translating hints into formula, deciding how to deviate from recommended values, and assigning weights to those hints. The observation that we're getting is, first of all, the text that we find in the input text documents, as well as natural language labels that are associated with specific actions and represent their semantics, because the actions of the agent are controlled by a pre-trained language model. So we want to express all those observations as text. Finally, the reward values are, first of all, given for constructing configurations that are not rejected by the database management system. And then, of course, for improving performance compared to the default configuration. Now, the environment in the context of reinforcement learning is represented as a set of states and actions that lead from one state to the other one. So in the context of this problem here, I'm modeling the environment as a decision tree, which essentially encapsulates all the decisions we have to make for a specific hint, like the hint that you see over here. So in the first level of the decision tree, we're deciding how to translate the given hint, whether we believe that this corresponds to an absolute value recommendation or whether this is a relative value recommendation that depends, for instance, on the amount of RAM available. The second level of the decision tree is associated with how we want to deviate from recommended values. And the last level of the tree is associated with how we want to assign weights to specific hints. In order to make choices here, the agent needs to obtain observations as input. And here the agent has a neural network that is very good at natural language processing. So we want to express those observations in the form of natural language text. Now, the first part of those observations that should be the text of the hint that we are currently considering. But beyond that, we also have to associate those different states in the decision tree with natural language labels that represent their semantics. So for instance, for the state that, that decides essentially that this hint should recommend a value that depends on the amount of RAM available, we would associate that state with a natural language label that expresses the semantics, such as the one that you see here. And those pre-trained language models are already very good out of the box at comparing pairs of text snippets in order to decide whether they are related. So if we are expressing observations in this way, then we can heavily benefit from the pre-training that the model we are using has received. In terms of rewards, we can already assign a reward value for translating hints into recommendations that are actually accepted by the database management system. Later, we will also assign reward for improving the performance. Now, in each iteration of the learning phase, we are considering multiple hints, a batch of hints in the order that we have determined during pre-processing. So here we are considering one of those hints. We would directly continue to the next hint and make decisions for this hint over here, which recommends an absolute value for the work mem database system parameter. And maybe we would still consider another hint in the same episode here about the maximum parallel workers. Of course, I'm only showing some part of this huge decision tree that we are searching here. After we have considered a couple of hints, we will finally try to construct one or a small set of configurations based on the decisions that we have made in the current reinforcement learning episode. We would evaluate this configuration in a trial run and measure the performance metric that we care about. And then finally, we would assign a reward value that represents by how much we improve over the default configuration. Then the current reinforcement learning episode ends and a new iteration of the learning phase starts with potentially a new set of tuning hints. But we will leverage the experiences that we're getting here in order to fine tune the weights of our neural network and hopefully make better decisions. All right. So perhaps the only step here that requires a little bit of explanation is how we integrate those possibly conflicting recommendations into one or a small set of configurations that we want to try out in the current iteration. Now, generally, we might have a situation like the one depicted here. We have multiple conflicting recommendations for the shared buffers parameter, here represented with the associated weights that we have assigned via reinforcement learning. And typically, we don't have enough time to actually try out all of those different recommended values. So we have to somehow select a subset of them. And the goal here is to select a subset that covers the proposed values as good as possible under constraints on how many of those values we can select. And in the case over here, we want to essentially select a subset of recommended values that minimize the maximum distance between any recommended value and the closest value that we have actually tried out. So for instance, here, if we select the two values in the middle in order to try them out in a trial run, then there's the leftmost recommendation recommending 20% with a weight of 8. So that hint is considered important. And this one is not very well covered because we have a distance of 10% and we have a weight of 8. So that makes a weighted distance of 80%. On the other side, if we select those two values over here, then our coverage is better because the maximum distance appears for the recommendation of 40% of RAM, which has a distance of 20% to the nearest recommendation. The associated weight is only 2. So here we have a significantly better coverage of all the recommended values. So this is the learning phase. We keep iterating until the user-defined time limit on optimization time runs out. Now, the implementation of DB-BERT is using Python 3. You can find the corresponding code in this GitHub repository that you see at the bottom of this page. It uses the Hugging Face Transformers library for natural language processing, and for reinforcement learning, it currently uses the autonomous learning library, now switching to the stable baselines library. The focus of the experiments is to show that the hints that we're extracting from text can actually be helpful in order to speed up a database tuning. So we focus on scenarios where we want to have a relatively moderate tuning time in the order of minutes. And we want to avoid any additional input that restricts the set of parameters considered or that it chooses parameter-specific value ranges to consider during tuning. So we will just consider all parameters of the database management system that either accept Boolean values or integer values. Those are the parameters currently supported. And as value ranges, we will just consider everything within a certain tolerance of the default values. And I'm going to vary this tolerance in the following. I'm going to show how to optimize Postgres 13 and MySQL 8 in the following. Both of them have hundreds of parameters that we'll consider for tuning in the following. The target workload are the TPC-H and the TPC-C benchmark, and we are experimenting on a platform with a relatively powerful GPU, Tesla V100, and 61 gigabytes of RAM. The compared algorithms are, first of all, the DDBG++ algorithm, which uses reinforcement learning, but no natural language analysis. Then the keywords-based and the supervised learning-based text extraction method, which extract tuning hints only by considering text documents, but without making any trial runs. And finally, there is DB-BERT, a system which combines information mined from text and corresponding and knowledge gained by executing trial runs. As input text, I'm using the following, essentially what we get by issuing the Google query Postgres performance tuning or MySQL performance tuning and extracting all text we get from the first 100 hits. So we are creating two different document collections, one for MySQL and one for Postgres. And initially, I pointed out that I'm using a heuristic, which is based on the frequency at which different parameters are mentioned. Here, you see a little plot about how often different parameters are mentioned. And indeed, it turns out that for both Postgres and MySQL, there are a few parameters which are very regularly mentioned, while most parameters are mentioned quite infrequently. The most frequently mentioned parameter for Postgres is the shared buffers parameter, which in my experience is quite relevant for performance. For MySQL, that's the InnoDB buffer pool size, to which the same applies. Now here we have, for instance, results when tuning a TPC-H with the MySQL database. On the x-axis, we have optimization time. On the y-axis, you have the execution time of the best configuration found until a certain point in time during the tuning session. And here I'm comparing DB-BERT with multiple versions of the DDBG++ baseline. You see this little number in parentheses behind the name of that baseline. This is the tolerance factor by which we deviate from the default parameter settings. So DDBG++2, for instance, considers value ranges for parameters that are 2 times lower and up to 2 times higher than the default settings. And as you see here, for the baseline which doesn't exploit any tuning text, it is actually hard to improve at all over the default configuration in this setting. The approach which mines tuning hints via a simple keywords-based method is not able to improve over default configuration either. The version that uses supervised learning is able to improve over default configuration a little bit, but not that much, and it takes quite a long time until it returns a first configuration. So the keywords-based and the supervised text extraction are non-iterative. This is why they're represented as one single dot in this graph. And by the way, the fact that the supervised learning approach, it takes such a long time to return a configuration at all, also motivates the need for not applying natural language processing on the entire collection of input documents, but rather to consider a few hints and then make some first trial runs with that. And as you see here, DB-BERT is able to very quickly construct configurations that improve significantly over the default settings, cutting execution time on the TPC-H benchmark by more than factor 2. We see similar results for the Postgres database system when tuning a TPC-H. So again, we find the best configurations with DB-BERT, even if the absolute improvements are a little bit lower. The same tendencies apply if we increase the scaling factor for TPC-H. So far, I have shown results for TPC-H with scaling factor 1. This is TPC-H with scaling factor 10. And similarly for TPC-C, where we care about throughput, so higher is better in those plots here, DB-BERT finds significantly better configurations compared to the default settings within a relatively small amount of optimization time. This is the same results when optimizing TPC-C on Postgres, and we see that in all of those cases, the additional knowledge mined from text documents help to construct the interesting configurations significantly faster than if you just try out things randomly. Also, if we look at the configurations that we find for the database system Postgres for TPC-H and TPC-C, we see that DB-BERT actually finds different configurations for those two different benchmarks, even though it considers the same collection of input text documents. And that shows that it is able to prioritize the hints that it finds in those documents in a manner that is workload and benchmark specific. So for instance, for TPC-H, we benefit a lot from parameters that increase the degree of parallelism for specific operations, as well as from increasing the setting for the shared buffers parameter. While for TPC-C, there's a couple of other parameters that are more important. I have also tried out a couple of different variants of DB-BERT. For instance, what happens if we don't prioritize hints during the pre-processing stage and just process them in random order. This is the green line that you see here. And it turns out that this actually degrades performance. It takes longer to find interesting configurations. Equally, if you don't consider implicit hints, it takes DB-BERT longer to find interesting configurations. I also gave it a try, and instead of providing a large collection of generic documents for database tuning, what happens if you provide one single document, which in this case is a discussion extracted from Stack Overflow about how to tune Postgres for TPC-H, which is exactly what we want to do here. And if we do that, if we replace the generic collection of documents by a more specific document, then indeed we find good configurations even faster than when using generic text as input. Now, we have already seen now that we can extract the interesting information for database tuning from the database manual and related text documents. So going forward, I want to see whether we can extract more information, for instance, about risks that are associated with specific parameter settings. There are certain parameter settings that cause, for instance, data loss in very rare circumstances, which is very hard to observe during trial runs because it is rare to happen. But the manual is actually very good at providing corresponding warnings, and using natural language analysis, I believe that we can extract them. I'm also currently looking at other entities in the context of databases where we can use natural language processing to extract useful information. For instance, we recently had some results on trying to leverage information gained from column names alone in order to prioritize data profiling approaches. Perhaps even more importantly, I think that natural language processing can improve the interaction with users in the context of database tuning. We can, for instance, try to parse natural language instructions from users about which performance trade-offs are desirable or which risks are acceptable. And of course, we can try to better explain to users why specific parameter settings are recommended. The models that I've used so far might not be powerful enough for that, but I'm currently experimenting with the GPT-3 model in the Codex version from OpenAI, which is significantly larger than the models that I've been using so far. And the first results look quite promising. And beyond this project on natural language usage for database tuning, there's multiple other projects that are currently ongoing in the lab. Here you see some of the projects that my students have recently published about. And as you see here, several of those projects are about database tuning or use a natural language analysis in some way. So this project that I have discussed today kind of connects multiple research streams that we are currently interested in. So as conclusion, I believe there's various interesting applications for natural language processing in the context of database tuning. I've presented the first tuning tool named DB-BERT, which exploits information mined from database tuning text. You find the code online on GitHub, and there's a couple of vision papers that I have recently published on the topic if you want to learn more about it. Thank you very much for your attention. And now I look forward to your questions.
Kind of on time. Any questions? Let's take one question because we kind of on time.
Yeah, I have a question. Why do you formulate the problems as RL problems?
Why we formulate it as a reinforcement learning problem? Okay, so the question is like which other framework we could use for that. I mean, reinforcement learning seems quite natural because we want to integrate information that we gain at runtime. So, I mean, we can get information about the performance for a specific configuration by just setting the corresponding parameters and then trying out the example workload and measuring performance. But it is a priori unclear what kind of configuration we want to try. We have the so-called dilemma between exploration and exploitation because we might be tempted to exploit configurations that seem to work well currently, and we want to construct similar configurations to that. On the other side, we might also be tempted to explore and to try configurations that are very dissimilar to things that we have tried out before. So there's a tension, and reinforcement learning essentially gives you the tools to balance that attention in a principled manner. So the scenario that we have here, which integrates the results of live trial runs, seems to match best to reinforcement learning. And that is also the machine learning framework that most of the other recently proposed methods in that space, which do not use a natural language processing, are using as well. For instance, the DDPG++ approach that we have used in the experiments, that one also uses reinforcement learning.
Okay, let's thank the speaker again.
Awesome.
Awesome, thanks.
All right, thanks a lot for the invitation.
Let me close.